less blockchain, or in public blockchain, the user base will be quite huge, quite large, and the requirement is also varied. The domains in which the transaction will be performed is also different. So it won't be like this that only transaction in one domain is being performed. So varied kind of requirements will be there, and it will be available to large number of users. So this is scalability when compared to permission blockchain. In permission blockchain, we only have a vetted number of users, a predefined set of users who will be accessing the blockchain. So their number of users doesn't matter. So scalability in permission blockchain will be in terms of transaction throughput. Maybe how many, and not in terms of nodes. So because we only have a few users or some set of users who will be accessing that blockchain. Coming to consensus mechanism that is being used in permissionless and permission blockchain. In public or permissionless blockchain, we generally use proof of work or proof of stake. So here in a proof of work, because it was first used by Bitcoin, and to ensure or to implement the consensus mechanism. So because it is a public blockchain, we need to ensure a strict consensus mechanism so as to uh, avoid the unwanted elements to participate in the blockchain, and only the genuine participant should take part in the blockchain. So for this to ensure, they have implemented the proof of work in such a way that it needs very huge computational resources. So those resources, huge computational resources or high computational resources, are not easily available for everyone. So only those users can take part in the uh, blockchain who has those high computational resources available with them, and who can solve that cryptographic puzzle within a stipulated time, so that they can win the puzzle and take part in block mining and all those things. So proof of work is a very strict consensus mechanism, and it is being used in this permissionless or public blockchain. And we have one more mechanism, that is proof of stake over there. So here the uh, the priority or the order is decided based on the number of bitcoins a user is holding. So more the number of bitcoins are being held by a user, he will get the priority. So this is a bit liberal consensus mechanism as compared to proof of work. But because we are working in a permissionless blockchain, so proof of work is as compared to proof of stake is preferred, so as to avoid the unauthorized user to access the blockchain. So in permission blockchain, closed membership consensus algorithm are used. So here very strict consensus mechanism are avoided, because because here the users are known to everyone as compared to permissionless blockchain. So there is a user in the permission blockchain is bound to act in a parliamentary manner, because his identity is known to everyone. Then we have identity management. In permissionless blockchain, it is anonymous or pseudo-anonymous. But in permission blockchain, identity of nodes are known, but the transaction identities can be private, anonymous, or pseudo-anonymous. So, so nodes identities are known to everyone, and in permission blockchain. Then assets, we have native assets here in permission less blockchain, and any asset or data state can be used in the private blockchain. So moving on, so just To conclude here in permissionless and permission blockchain, so in public or permissionless blockchain, note that you don't need to sign up, log in, or apply to join the network. You can just go ahead and join in. Compare this with the Swift network, where you can't just download some software and start listening to Swift messages. In this way, some call Bitcoin permissionless versus Swift, which would be permission. So, so Bitcoin is used to perform transaction on a public blockchain, and you need the users like you and me can also take part in this public blockchain, and we can start mining the nodes over there. So that is readily available online. We can download that public blockchain, and I think it needs some 200 GB of space, and few more requirements are there. So the only bottleneck is how to solve that cryptographic puzzle that needs huge computational resources. As compared to permission less blockchain, we have private blockchain. So you may want to use blockchain technology in a trusted private network. So you may not want to publish all the rules of what a valid transaction or blocks looks like. You may want to control how the network rules are changed. So it is easier to control a trusted private network than an untrusted public free for all like Bitcoin. So because I have said in my previous slide also, so if you want to change some rules, so you need to change your requirement as per the public blockchain. But in case of private blockchain, you can get the customized private blockchain as per your requirement. So many players like Microsoft, Azure, IBM, they are ready to give you blockchain as a service as per your requirement, as per your needs. So you just have to tell them your requirement, and they will give you a customized blockchain so that you can take over your business completely on the blockchain. So if you want an easily maintainable, manageable, less overhead, so you better go for private blockchain, where the rules can be managed as per your requirement. You can frequently change your rules if the need arises. You can control how the network rules are changes, and everything will be under your control. So this is something about permission and permissionless blockchain. So it depends on your requirement and on your capacity, and how you want to manage that blockchain. So according to your application requirement, you can select the blockchain and you can start using that one. So moving on, there exist few myths or misconceptions, you can say, about blockchain. So I have identified from some sources that these are the 5 myths that are very common about blockchain. So first myth is blockchain is a Bitcoin. So so in my previous slide also, maybe at some point of time you may think that blockchain and Bitcoin is one and the same thing. So this is not the same. Bitcoin is a cryptocurrency, and Bitcoin is used to perform transaction on blockchain. So Bitcoin is just one cryptocurrency application of blockchain. It is considered as an application of blockchain. Blockchain technology can be used and configured for many other applications. So we have many other Bitcoins or many other cryptocurrencies, all currencies that are prevailing today. So blockchain is not a cryptocurrency. Blockchain is Bitcoin is a cryptocurrency, and there exist many applications of blockchain. Okay. So we can use those cryptocurrencies to perform transaction on blockchain. Blockchain is better than traditional databases. So reality is that blockchain's advantage come with significant technical trade-off. So that means traditional databases often still perform better. But blockchain is particularly valuable in low trust environments where participants cannot trade directly or lack of an intermediary. So Look, intermediary is always there. So right now, if you are even if you are performing a transaction today, some intermediary is there. So most of the time, intermediary in our case is banks. So in cryptocurrency, you are basically ruling out that intermediary. Okay, without the any need of intermediary, you are performing the transactions, but there is a high risk. Okay, and the environment is trustless, or you can say low trust is there. Okay, and there is no intermediary in between. So a kind of trade-off is there. If your application, it depends on your application requirement. If your application requirement or if your application is acceptable with low trusted environment and without any intermediary, it works fine, or you are good to go, then you can go for the blockchain. So in case you have you are working with some sensitive data and you feel that there are high chances we are not sustainable to risk, then you can better go for some traditional databases. So it's a kind of trade-off. So it depends on your requirement. So the things are inversely proportional. Whether you look as per your requirement, whether you want high risk, high security kind of trust you want. So things are not directly proportional, things are inversely proportional. So a trade-off is there. So if high risk is there and you don't want to get high risk, then better you go for some other traditional databases. So if you want, if you are good with working with low trusted environment, you can go for blockchains. Next one is blockchain is immutable or tamper proof. So blockchain data structure is append only. No data can't be removed. So you can just append your data in the blockchain, and even if someone tries to tamper that tamper with the blockchain block will get invalidated. And once a will get invalidated, the whole blockchain in turn will get invalidated. So blockchain could be tampered with if greater than 50% of the network computing power is controlled and all previous transactions are rewritten, which is largely impractical. So it is very close to negligible, means the probability of getting the blockchain tampered or make the blockchain invalid is very less, because for this for a blockchain to tamper, you need to acquire 50% of the network computing power, and all the previous transactions are needs to be rewritten. So this is quite close to impractical. So practically this is not possible that you can tamper the blockchain. So it is an append only, and data can't be removed. So this is very much so means it cannot be tampered. So this is true that blockchain cannot be tampered, and it is immutable. Blockchain is 100% secure. So blockchain uses immutable data structures such as protected cryptography. So overall blockchain system is secure, and security depends on adjacent application which have been attacked and breached. So nothing means though there are several cases in the past where blockchain has been attacked, and it also depends on the type of application you are using to access the blockchain. So we can't ensure that security is 100%, because there are malicious users present all over, and if some financial incentive is given to someone to to break the chain, or to ensure or to creep in the denial of services, so things can be done in that way and manipulated. So though it is secure, but saying that it is 100% secure, so again I would say that it depends on the application. If your application is can sustain risk or security attacks, then go for blockchain. And if you are working with the critical application, so accordingly you have to take the decision whether you have to go for blockchain or some other applications. Blockchain is a truth machine. So blockchain can verify all transactions and data entirely contained on and native to the blockchain. So blockchain cannot assess whether an external input is accurate or truthful. This happens to all of chain assets and data digitally represented on the blockchain. So it's truth in the it's a truth machine in the sense that you can verify the transaction that has happened on the blockchain. So it is easily available in the public blockchain to everyone, and it is easily accessible to a set of users in a private blockchain. So you can just verify about the authenticity of the transaction. Yes, the transaction has been happened, has been done on the blockchain. So, but uh, other than this, nothing can be assessed about the transaction. Only we can check yes, the transaction has been done on the blockchain. So these are few myths. Some of them holds true and some of them does not holds true. Like myth number one, blockchain is a Bitcoin is false. Myth number two, blockchain is better than the traditional databases. So it depends on the application requirement. Blockchain is immutable or tamper proof. This is true. Blockchain cannot be tampered. Blockchain is immutable. So it will get invalidated if someone tries to tamper it. Blockchain is 100% secure. Again, it depends on the type of application where for which you want to use the blockchain. Blockchain is a truth machine, so it will just tell you whether a transaction has taken place or not, whether a transaction is valid or not. Now, though you must have already discussed this consensus mechanism in your previous session, so I will just have a quick overview on this one consensus mechanism, as it plays an important or vital role in this blockchain. So it's a consensus is a procedure to reach in a common agreement in a distributed or decentralized multi-agent platform. So as we have already discussed, and so it is nothing but we are taking or we are reaching the mutual agreement, and in a decentralized multi-agent platform. So multi-agent platform means when there are multiple miners are working simultaneously to mine the block. So we need to take the consent of every other miner before adding that block to the blockchain. So for that we have consensus mechanism in blockchain. For example, there are four people who could make two decisions, A or B. Three people who are in favor of A and one person who is in favor of B. The decision A will be considered as majority of people are in favor. So this is very much clear. We generally use go with the majority voting. So if majority voting is in favor of A, we'll go for A, and if majority voting is not in favor of B, we will not go with B. So there is a need for consensus, reliability, and fault tolerant distributed system. Even if there are certain faulty nodes present in the network, correct operations can take place using consensus. So we have different type of faults here: crash fault, network or partition fault, like Byzantine fault. So this is we are discussing because we may have faulty nodes also in our network, and a node suddenly crashes or become unavailable in the middle of communication due to some software or hardware. We basically call it crash fault. And network fault that occurs and the network get partitioned. And Byzantine fault, node start behaving maliciously. So this is the most serious kind of attack fault we have here. That is the Byzantine fault. So, and this is very difficult to predict and identify the malicious node. And these type of faults are identified, but after some amount of time has been passed. So after closely observing the behavior of some node, only then this node can be identified that this node is involved in malicious activities like overcrowding the network, like inducing the denial of service attack and some kind of these attacks. Nodes can be identified as the malicious node, and this node should be uh, barred from the network. So uses of consensus. So if you wish to transfer some money from your bank branch to some other bank branch, then all bank branches needs to reach consensus to decide the validity of transaction and then allow the transaction. So it is used for state machine replication, and it is used for clock synchronization. So in distributed consensus, it is the process by which peer agrees to addition of next block in the blockchain. So distributed consensus ensures that different nodes in the network see the same data at nearly same point of time. Hence, in case of any failure, the system can still provide the services as data is decentralized. To maintain anonymity in this large network, a permissionless protocol is used where you don't need to record your identity while participating in the consensus. So this one is very important in blockchain. As I have told you earlier, we are working with a decentralized peer-to-peer system. So in decentralized peer-to-peer system, there is no single authority or no single point of failure. So it is not like this that some nodes are shut down, so our system will come to halt. No, the case is not the same here. Our system will also keep working in case of failures because our system is a decentralized peer-to-peer system. So this is what they mean by distributed consensus. They are saying that it is a process by which peer agree to addition of next block in the blockchain, because miners are mining the blocks and they are fighting to get their blocks added in the blockchain, but only one miner will get the chance to add its block in the blockchain. So this distributed consensus ensures that different nodes in the network see the same data nearly at the same point of time. So if this means to say that because the blockchain is replicated on multiple miners with multiple miners, and we have created the replicas of the blockchain. But as this blockchain is keeps updating, so we need to ensure that every miner is having the updated copy of that blockchain. So no miner is working with the stale outdated copy of the blockchain. And again, this is the issue of consistency. So this consistency of blockchains replica needs to be maintained. So this distributed consensus ensures that in case of failure, system can still provide services as data is decentralized. So this is the biggest advantage of decentralized system. So even in case of failure, the system will keep working because only one node has down and rest of the nodes are up and working. And every node has the capability to provide same set of services. Then we have few properties of distributed consensus like termination, validity, integrity, and agreement. So every correct node or non-faulty node decides some value at the end of the protocol. So the validity, if all the individual proposes the same value, then all the correct individual decide on that value. The integrity is something about every correct individual decide at most one value, and the decided value must be proposed by some individual. In agreement, every correct individual must agree on the same value. So these are the few properties: termination, validity, integrity, and agreement of distributed consensus. So it is all about reaching the consensus. You're taking the consent of all the miners in the blockchain. So without their consent, we cannot move further or we cannot add our block in the blockchain. Once the consensus has been received by all from all the miners, we are ready to go and add our block in the blockchain. So when I usually says talk about this one Bitcoin, yeah, adding the block in the blockchain. So this is I've told you earlier also we need to solve in a puzzle, cryptographic puzzle. So this is basically better known as challenge response system. So network poses a challenge and each node tries to solve that challenge. Challenge is nothing but a cryptographic puzzle that will be solved by each miner. A node which solve the challenge first get to dictate what set of data or state elements to be added in the network. This process continues iteratively and ensures that different nodes win the challenge at different runs. Hence, no single node will be able to control the network. So, this cryptographic puzzle is designed in such a way so that it ensures that different miners will keep getting the chance every time, and the control is network is not controlled by single node. So monopoly kind of things are not there, and no monopoly is acceptable here in blockchain. So this Bitcoin proof of work algorithm ensures consensus over a permissionless setting based on challenge response system. Every node spends large amount of computational power to solve mathematical challenge in each iteration of the consensus. So this computational effort expended by the nodes in achieving consensus would be paid off for by cryptocurrency generated and managed by the network. So this Bitcoin, this uses proof of work algorithm. So this in proof of work algorithm here, a cryptographic puzzle, or you can say a mathematical challenge is given to the miners, and they are involved in solving that challenge at the earliest. So the miner whosoever solves the puzzle first will get the chance to add the block to the blockchain. So this message passing system is being used because as you know, when we are communicating with the entities, we can either use shared memory or we can either use message passing system. So as you can see that we don't have any dedicated infrastructure here. So where the shared memory will actually exist or resides. So the best way to implement uh, is message passing system. So message passing is a technique for invoking behavior on a computer. So the invoking program sends the message to a process and relies on the process and supporting infrastructure to select and invoke the actual code to run. So in message passing system, we have different type of message: synchronous message passing system and asynchronous message passing system. So in synchronous message passing system, the delay time is also guaranteed. So it is used by Paxos, Raft, Byzantine fault tolerance, and some synchronous consensus algorithm explored by distributed system community. So we have this synchronous message consensus algorithm here in blockchain. And in asynchronous message passing system, message can be delayed for arbitrary period of time. No fixed message reception time is decided. So one more case is there of impossibility result. No consensus can be guaranteed in a purely asynchronous communication system in presence of any failure. In such system, consensus may occur recognizably, rarely, or often. So in impossibility result when we don't receive the consensus due to failure or any other factors. So in that case, if the consensus is not received, we cannot move further. So so this message passing system, this required a closed environment. So everyone need to know the identity of each other. So we cannot implement this message passing system in an open environment. Since Bitcoin, anyone can join the network. So that is mostly used in a public blockchain, or you can say it mostly used in open environment. This clearly is not possible in a open environment. So shared memory is not suitable for internet trading community, where we will keep the standard shared memory. So this is an issue with the open consensus system. So how we take the consensus in open system? So consensus in open system is taking with the, again it is taking with the help of proof of work. So all nodes in this network need to agree on the correctness of transaction. Some nodes can also initiate malicious transactions. Whenever multiple miners mine new blocks simultaneously, the objective of consensus is to decide which block is to be added next. So अगर simultaneously there is a tie, or though chances are very rare, but in case two miners have simultaneously mined some blocks, or two miners simultaneously have win the cryptographic puzzle, so they have their chance to add the block in the blockchain to the blockchain. So only one miner will get the chance to get the block to the blockchain, and another miner, the block mined by the another miner, will become the orphan block, because we don't have any other mechanism over here. So here miners don't know each other because it is an open system and public blockchain we are working with. If we broadcast the transaction, then the impossibility result might occur because we don't have the global clock, so it is not feasible to wait for infinite time. So every miner solves the challenges independently. The miner who completes the challenge first will add the block mined by him to the blockchain. So this is his proof of work. Now the miner sends the solution to all the other miners, and this block is included in the blockchain. So once the miner gets the consent from the other miners, he is ready to go and add the block in the blockchain. In case any transactions are not logged in by the block, they will get included in the next round. So usme there are chances that some transaction will get added to the block and some may be ignored. So need not to worry about those transactions that are not added to the block, because block has some limits by its size or by number of transactions. It depends on the block size and how you have implemented it. So that transaction will be added in the next block, and whenever that next block is added to the blockchain, the transaction will be visible to everyone. So this is a miner who
Sir,
has
how the miners?
yeah. What are the miners?
Sir, can I ask a question?
Yeah, please.
Sir, how the miners verify whether the block that was created by a random individual can be added to the blockchain or not? So
So
we actually I heard the term that miners verifies the block which is created by an individual,
yes.
but how the miners verify, I do not understand.
Yes. So what once a transaction is being done by an individual, suppose you and me are performing some transaction on the blockchain. So miners are the entities who are responsible for verifying the transaction on the blockchain. So because if we are working in public blockchain, all the transactions are available on the block, and miner will just check whether the transaction is being done or not. So it is the responsibility of the miner, because once you if you are acting as a miner, you need to get that blockchain on your system. So once a transaction is being performed for any commodity, so that transaction is being stored somewhere in our database. So the miners, it's the responsibility of miners to ensure that uh, that transaction has happened, so and that transaction has taken place. So miner will search in the transactions and validates whether a transaction has taken place or not. So once the miner has look for the authentication of that or look for the validity of that transaction, and he verifies that transaction, so now the next task for the miner is to uh, take the consent from the remaining miner to and he will add the transaction to the block. So he will keep on adding on keep on validating few transactions or n number of transactions like this. So once he has the block has been created by him, now he need to take the consent from every miner to add that block to the blockchain. So miner will just act as validating the transaction that is being done by you and me over the blockchain. So he will just check the credentials, like the amount of transaction, the commodity for which the transaction has been done, and the time at which the transaction has been performed, and few more attributes whatever are available there. So it is just all about the verification of a transaction, whether a transaction is valid or not, and whether the same transaction has not been done twice. So to avoid the double spending problem, which is a issue here in this blockchain. So once a miner verifies a transaction, he will add that transaction to the block, and similarly he will verifies n number of transactions. So he will keep on verifying the transaction and keep on adding those transactions to the block. So sir, did I solve your issue a bit?
Actually, sir, my question was that we are performing a transaction. We
Huh?
perform the transaction. The miner checks our transaction. He creates a block. When he
He
creates a block, we are
Huh?
sure that he has created a block. Now he
Hmm.
distributes that block across the network for consensus. So
No, no.
actually, I wanted to know how
Uh,
the other distributed nodes in the network would come to a consensus. So what is the procedure for that consensus, I am asking, and how they would validate the block that I have created is not a forged block or an invalid block.
Yes. So actually, if we have if one miner has created some block, so that block contains some n number of transaction. So now the first thing is that if some miner is getting a chance to add a block to the blockchain, so before that he must have this cryptographic puzzle. Okay, and this in public blockchain, so it is not easy to win that cryptographic puzzle. So the miner who is getting a chance to add that block in the blockchain, because to win this cryptographic puzzle he has spent a lot of resources in terms of time, in terms of computation. So this miner will for sure will not try to add some forged block, because he has already spent a lot of resources to win that cryptographic puzzle and to get the chance to add the block in the blockchain. So this is one thing. So once he has got the chance, and after spending a lot of resources to add a block in the blockchain, so he intentionally will not add or try to add some kind of forced block or some kind of malicious activity. So he will not involve himself in those activities. This is one thing. Another thing, once he has added the transaction to a block, so now he will take the consent from every other miner to add that block to the blockchain. So all other miner in the same way will validate the transactions, and they will give their consent uh, to the requesting miner. So it depends, because consensus algorithm is something that depends on the type of application we are using. And in the upcoming slides, in a couple of after a couple of slides, I will show you a, 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 a blockchain a diagram where you will get to know how the consensus mechanism are being used in blockchain. It totally depends on the requirement that we can use the consensus mechanism. So your question is that how we are distributing this block, and how the other miners are giving their consent. So this because a block is added once we have got the consent from other miners. So before adding the block, we need to take the consent from the remaining miners in the network. So remaining miners will give their consent by validating the transactions in the block, and once they have validated the transactions in the block, they will send their consent to the requesting miner. And once he has got the consent from all the miners, he is good to go, and he will be able to add the block to the blockchain. If you still have more doubts, I can take it after the session. No issue with that.
Sir,
Okay.
any questions will be after the session, sir? All
Uh,
questions will be after the session, sir.
it will be good for the remaining participants, because otherwise, if it is
Okay, sir.
It will be
Okay.
good for the
Thank you,
remaining
sir.
parts. That's why we are using that practice. So moving on, so how Bitcoin approaches some of the decisions. So because Bitcoin, we are using this cryptocurrency in to perform the transaction on a public blockchain. So we have categorized few attributes like data storage. So question here is how should data be stored? So Bitcoin approach is it is stored on blockchain, and other ways that a database could also be used to store the data. Next one is data is distribution. So how should new data be distributed? So in Bitcoin, it is we are using peer-to-peer, and other ways we can use client-server hierarchical model, which we largely discourage in Bitcoin or in blockchain. Then consensus mechanism. How should conflicts be resolved? So like we have seen, there is a possibility of forming a blockchain tree. So in Bitcoin we follow the longest chain rule. So we consider longest chain as the valid chain, and other chains will have the orphan blocks, and those blocks will be sent back to the mining pool, and they will be mined again. And other ways, non-needed in trusted networks. So because if we are working with private blockchain or permission blockchain, so slightly diluted consensus mechanism can be used. So upgrade mechanism, how the rules can be changed. So as I have discussed earlier also, in permission in public blockchain, rules are not very frequently changed, and you need to change your requirement as per the public blockchain. But even if it is not like this, the rules are never changed in public blockchain, they are changed. So for that, in specifically in Bitcoin, we have Bitcoin improvement proposal. So they are responsible for performing the writing the rules and and upgrading the rules or mechanism. But they are not very frequent because it is a public blockchain, and it is not very easy to change the rules very frequently. So as compared to other ways, centralized upgrades or contractual obligations are there. And permission blockchain, there are rarely any changes, or very less changes are there. Then we have participation criteria, who can submit transactions. So in blockchain, anyone can perform the transaction. They are totally pseudo-anonymous. And in permission blockchain, we have pre-vetted participants. So their identities are known to everyone. And we have only very less user base in permission blockchain. So again, in the same participation criteria, we have who can read the data. So again, in Bitcoin, we have pseudo-anonymous, and in permission blockchain, only a trusted set of user can read the data. Then who can validate transactions? So in Bitcoin, you and me can also become the miners, and we can start validating the transactions. But in case of permission blockchain, we have some predefined set of users. So then we have defense mechanism, how to prevent the bad behavior. So we usually use proof of work. So because we prefer this one because of its strict and huge resource requirement, so that we can rule out the involvement of malicious users. So that's why for defense mechanism, we usually use proof of work in public blockchains. And in private blockchains, we don't need very stringent or strict consensus mechanism, because users are already known, and we have a very small user base, or trusted set of users are there. Then incentive schemes. So how to incentivize block makers. So this one is very important, and this has changed over the time, gradually change over the time. So only expensive in Bitcoin because of proof of work. So as I have told you earlier, because proof of work is involves or is very complex, and it is a quite expensive operation, because you need to spend a lot of computational resources that involves your electricity and all such stuff also. So, and cost on infrastructure and many more things. So if someone is a someone tries to misbehave in public blockchain where proof of work is acting as a consensus mechanism, so it's really means pity on him, because he's or someone is trying to befool himself only, and while involving a huge amount of resources and cost, and that too for without any objective, because he will, if someone tries to act maliciously in a public blockchain, he will not he won't be able to receive anything beneficial in turn. So it's a completely a wastage of computational resources, cost. So this one is very expensive task. So in terms of private blockchain, so contractual obligation, third party funding is there. So or it's kind of sponsorship you can get, something like that. So how to incentivize blockchain data storage? So it is not considered in Bitcoin. And how to incentivize transaction validation? Again, it is not considered in Bitcoin. So these are the approaches that Bitcoin takes, and Bitcoin being a cryptocurrency that is being used over a public blockchain, and how the decisions are made there. Now, coming to this one, so this one is the decision tree to choose the appropriate consensus algorithm. So as I was discussing in my previous slide, so about consensus mechanism. So it depends on a lot of factors, on a lot of parameters, that what consensus mechanism should we go for. Okay, so it also depends on your application requirement. Okay, what is your application requirement, what exactly you need, and how much resources you have to implement that consensus mechanism. So first, it start with incentivization. Okay, whether you want your consensus mechanisms to be incentivized or not. If you want your consensus mechanisms to be incentivized, then comes the energy. And if you don't want your consensus mechanisms to be incentivized, then you can go for this one. If you select no, I don't want my consensus mechanisms to be incentivized, then you can go for RBFT, SBFT, YSC, POAT, Borough, something like this. So we have this acronyms definition in the next slide for your reference. Now, if you say you want your consensus mechanisms to be incentivized, then what type of energy you want, whether you want high energy or low energy. If you want your consensus algorithm to consume less energy, you can go for, again, you can go for this set of consensus mechanism, or you can go for this set of consensus mechanism. So these consensus mechanisms are considered to be incentivized with low energy. If you want medium energy, you can go for chain consensus mechanism. And if you want high energy, then comes the issue of scalability. Whether you want low scalability, whether you want high scalability, or whether you want medium scalability. If you want your consensus mechanisms to be incentivized with high energy and medium scalability, you can go for these consensus mechanisms. But if you want your consensus mechanisms to be incentivized with an high energy and high scalability, then you can go for these consensus mechanisms. So if you want high energy and low scalability, then comes the issue of security. Whether you want high security, whether you want low security, or whether you want medium security. If you want medium security, you can go for these set of consensus mechanisms. If you want low security, you can go for these set of consensus mechanisms. And if you want high security, then you have to go for proof of work. Proof of work is considered to be highly secured uh, consensus mechanism. Then again, in proof of work, whether you want AISC resistant, means AISC is a high computational server. So this is used to solve this cryptographic puzzles. So whether you want CPU bound proof of work, or whether you want memory bound proof of work. So this slide will give you an overview about selecting the type of consensus mechanism depending on your application requirement. Okay, and it is also a hot topic of research, and what kind of consensus mechanism you are going to implement in your thesis or for your application. So these are few decision making steps that you can take depending on your application requirement, that which consensus mechanisms to select for application. So these are the few acronyms which I have detailed here, like proof of research, proof of bond, proof of stake velocity, proof of cooperation. Then we have RESTs, SBFT, then we have delegated proof of stake. So these are the acronyms which I have used in the previous slide. So this you can I can give you the reference of this one. So this you can readily use for your reference if you are working on blockchain research work. So moving on. So we have 6 distinct categories of blockchain use case addressing 2 major needs. So these are the 6 different categories. They are divided into 2 categories. One is the storage of static information, and another one is the registry of tradable information. So in static information, we have static registry, identity, and smart contracts. So these are said to be static because they are not going to change quite frequently. Okay? So they are kind of permanent attributes that gets associated with that entity, because like your name, date of birth, gender, these are the few things which don't get readily changes. Okay? So they, once they get associated with you, they are permanent with you, so they remains there with you. So these are considered as static information. So the use cases, these are the use cases for this one. So information that we don't expect to change rapidly, but it gives you a view of history and also a point of view on ownership. The second is identity, means it is your identity, and that is not going to change quite soon. And third one is a smart contract. So a set of condition triggering automated self-executing actions. So it's a very good case study they have taken here in given in this. So यहाँ पर क्या हुआ था, to explain this the usefulness of smart contracts. In Australia, the farmers in many areas have not had enough rain. So if they had insurance contracts, these would simply automatically pay out on the basis of the limited amount of rain, and we have had in past month. So they have some IoT Internet of Things sensor on the field, and they have an insurance contract that payouts on a monthly basis depending upon the amount of rain received. So means this is means when I was going through this article, so I was very much impressed, and I included this here in my presentation. So this is quite useful and knowledgeable for you also, every participant over here, because India being a largely dependent on agriculture, and many farmers are there, and many agricultural land is available in India. So the same can be process can be implemented in India also. So it's not a big deal to get the things done. So why not farmers should have the liberty to get the automatic payout for any loss of for any loss in farming they are having because of natural calamities or any other reasons. So this kind of automated services or should be provided to the farmers for their smooth payouts of insurance and other things. So this is a kind of motivation we can give them with the technology. So let's why not let's get this technology involved in the farming. So this is a case study from Australia where they have benefited the farmers by making use of smart contracts. So so moving on to the next category, that is a tradable information. So tradable information, you can consider it uh, as the information which is changing quite frequently, like land registry, like payment infrastructure and other things. Okay, so this category means again there are multiple use cases will be there. So in every domain. So these are the few case studies which we have taken to for this category. So like dynamic registry, which you would mention is simply a database that updates as assets are exchanged. So this is example of things like trade finance. So there things are that are much higher throughput and does not very static. So the things are changing quite frequently. So it is consistently changing and the assets are moving around. Then payments, a lot of banks are experimenting with this around dynamic distributed database for payments, all type of including cryptocurrencies. Then we have many other things which are changing very frequently. So they came under registry of tradable information. So these are kind of use cases we can we have other case studies also like supply chain, like healthcare infrastructure, like e-voting mechanism. So we can categorize them either in the static information or tradable information. Oh, sorry, I got disconnected. So I was totally unaware that I got disconnected. Really sorry for the inconvenience caused. So, so I'm really sorry for the inconvenience caused, everyone. So we were discussing about the 7 design principles. So these are the design principles which are very much required for the smooth functioning of the blockchain. So I was discussing the first design principle, that is network integrity. So it's all about which says that the trust does not come from outside source. So that means that the 4 values of integrity, that is honesty, consideration, accountability, and transparency, are coded into a blockchain. They are baked into decision rights, incentive structures, and operations. Integrity is distributed among nodes and not vested in a single member. That means acting without integrity is either impossible or cost far too much money, energy, time, and reputation. So it says that cheater never prosper. To make sure this works, we need to first understand the problem with integrity online. On the internet, people have not been able to do business directly because money and other assets are not like the other things you can share online. Like you can share your image online and you can create a copy of that too, but you cannot create a copy of currency. Okay, so that is not possible to that you have once you have given the currency to someone, you can at the same time you can give the currency to someone else. So money must leave your account and go into your friend's account. It cannot exist at 2 places at the same time. If the internet traded money is just like information, there would be a risk if you are spending the same money twice, and this is called a double spending problem. So that's why till date it is not possible to send money over the internet. So we need to ensure that there should not be double spending problem. So it should not be like this, the same currency you are giving to 2 people for spending. So that's good for fraudsters, but it's bad for the people who deserve to be paid. So it is also bad for your reputation online. So traditionally, double spend problem has been solved by clearing every transaction through the third party. So this could be a bank, money transfer service, credit card company, government, and any online platform. So this is a kind of intermediary we are having in our case here, which is taking care of the transaction being done online. So we are not doing any transaction without an intermediary till now. So this means that giving all your information to someone else, it also means payments are settled on their schedule, not on yours. So of course, our money is in the bank, is in the hand of banks. Bank are totally aware of all our properties, all our transactions, all our money we have, all our salaries, and they, as per their convenience, they settle down our transactions. So it is not as per our convenience. So, so this one of the Bitcoin blockchain, the network timestamp, that first transaction where the owner spends a particular coin, it rejects any more spends of the coin, eliminating the possibility of double spending. And since the blockchain is public, Bitcoin is more traceable than cash. When network reaches the consensus about what happened, it records it on the blockchain. So how the network reaches the consensus is a critical factor. The Bitcoin network relies on what is called proof of work, because we can't rely on the identity of miners to select who creates the next block. So network instead creates the puzzle, and miner use their resources, namely computing hardware and electricity, to solve the puzzle by finding the right hash. And this puzzle requires a lot of computing resources to solve, but when someone solves it, everyone else can check the work quickly, and whosoever solves the problem will get the chance to create the next block. And after each block a miner creates, he or she will receive Bitcoin as a reward, and there are no shortcuts to solving the problem. So when the rest of the network sees the answer, everyone trusts a lot of work went into producing it. So it's a kind of something inherent in this solving the puzzle. So everyone understands that, or every other miner in the network understands that if he is able or she is able to solve that puzzle, so he or she deserves that. So everyone trust that he has put in a lot of work to produce that answer. So this trust is something inherent which is there in that proof of work or in that mathematical puzzle. So this proof of work, it rules out the possibility of malicious behavior being shown by some miner, because the miner has to spend a lot of efforts in solving that cryptographic puzzle. So what are the implications of these rules? So network integrity. Well, rather than trusting a big companies and governments to verify people identities and vouch for their reputation, we can trust the network. The history will be all there. It's checkable and it's unchangeable. So the platform ensures trust in transactions and recorded information, no matter how other party acts. And this has enormous implication on social, political, and economic activity. It is not just about recording who married whom or who voted whom or who paid whom. It's about any endeavor requiring trusted records and assured transactions. It can tell you who owns what, regardless of whether the property is physical or intellectual, who graduated from medical school, who bought which gun, who made this pair of shoes, and everything is there available there on the blockchain. So the first principle is network integrity. So everything is there in the network, and we need to trust the network because the network is designed in such a way that some things are inherent there. Second one is distributed power. So blockchain system distribute power across peer-to-peer network. There is no single point of control. No single party can shut the system down. If the central authority manages to cut off the individual or a group of system will still survive. Over half of the network attempts to overrun the whole. Everyone will see what's happening. The problem itself is centralization of power. So they override their wishes, they implement large scale changes without consent, and they warehouse and analyze their data. They also share those data with governments without users' knowledge, because they are so powerful they can do it pretty much without repercussions. So distributing power on blockchain restacks the deck. That's why it is a breakthrough. So there is no central authority here. For Bitcoin blockchain, for example, there can't be the energy cost of taking it over would outweigh the financial benefits. As proof of work mentioned, requires users to expend a lot of computing power, therefore a lot of electricity to defend the network and mint the new coins. So government could not arbitrarily seize assets on the blockchain as they have with physical currency. So in 1933, this Franklin Delano administration required citizens to turn their gold coin, gold bullion, and gold certificates over to government or risk fines or jail time. So simply put, the blockchain resides everywhere. There is no central authority. Volunteers maintain it by keeping their copy on the blockchain to update and lending their spare processing power for mining. So this is something about distributed power. And the implications that are involved here are distributed platform like Bitcoin. Blockchain can enable new distributed model of wealth creation and new kinds of peer-to-peer collaboration could target humanity most vexing and intractable social problems. Coming to third design principle, it is value as an incentive. So what does this mean? So, well, way blockchain is set up, it aligns incentives to all stakeholders. It uses a token of value like a Bitcoin to promote behavior benefiting the blockchain as a whole. So when everyone has a stake in the network, people make sure that it stays healthy. So the problem it solves is a destructive incentive system. So because now everyone has its own benefit, so everyone wants to prosper this blockchain. So this thing is demotivated. So there is no destructive incentive system now. The blockchain breakthrough is in using programming to incentivize good behavior. And Santoshi recognized that people act in their own self-interest. So he needed to harness that self-interest to build and protect the blockchain. So this value as an incentive is being given to the miners or to the user of the blockchain so that they can themselves protect the blockchain for their own interest. So this is what is recognized by Satoshi Nakamoto, that people act in their own self-interest. So this is being given, value as an incentive is being given to the people so that they don't harm the blockchain, they don't start behaving in a malicious way over the blockchain, they don't try to congest the blockchain, they don't try to induce denial of service in the blockchain. So some kind of these things are being ruled out with the help of value as an incentive when it is given to the users. So what basically is happening here, it is assumed that blocks created every 10 minutes. So more mining power is added to the network, block created far faster, so difficulty goes up and guessing takes longer. So we have to ensure that block should be created in every 10 minutes. It should not take less than 10 minutes, it should not take more than 10 minutes. If creating a block is taking more than 10 minutes, what we will do, we will uh, lower down the level of difficulty. If block is getting creating very faster, what we will do, we will increase the difficulty level. So we have to ensure that block should be created in every 10 minutes. So this is not for every blockchain. So it depends how much time you are taking to create a block. So the implications of using this value as an incentive. So with the blockchain, people have financial incentives to collaborate effectively and to create just about anything. If your reputation is valuable and trackable, online discussion groups won't be inundated with roles. Bad behavior will cost too much. So homeowners could receive real-time payments for using solar panels to generate sustainable energy for the network. So similarly, we have some security here. So to provide not only confidentiality but authenticity and non-repudiation to all activity. By non-repudiation, we mean the authenticity of records like digital signature can be denied. And typically, bank does not specialize in developing secure technology; it specializes in financial innovations only. So using public infrastructure from the start makes a long blockchain almost impossible to hack. So that's a blockchain breakthrough. So implications of blockchain security measures. So these days technological security goes hand in hand with personal security. Today bits can pass through our wallets and firewalls and wallets. So these can pick our pockets or hijack our cars from other side of the world. So as each of us relies more and more on digital tools and platforms, the threats have multiplied. So with the secure design and transparency of blockchain like Bitcoin, we can make transaction of value and we can protect our data. So means as our blocks keeps on getting older, it will keep on getting more secure. So this is just a case study to show you about the blocks being added. So this is the latest block, number 57 is latest added to the blockchain. So it is less secure as compared to block number 150, which is already added 1 hour before this one. So as our blocks will keep on getting older in the blockchain, they will become more secure because it will become quite difficult to tamper with them. And if someone tries to tamper with them, there is a possibility to get the blockchain invalidated. So this is next to impossible. Then privacy is also a design principle, fifth design principle, which we need to consider here. People ought to have right to decide what, when, how, and how much about their identities to share with anybody else. So privacy of one's identity, one's data. So it should be in the hand of the owner, on the people, that how much data should be shared to the public. So the blockchain breakthrough is in disentangling identity from transactions. So when Satoshi Nakamoto created the Bitcoin blockchain, he installed no identity requirements for the network layer itself. So no one has to provide a name or email address or any other personal data in order to download and use the Bitcoin software. So the implications of blockchain privacy safeguards. So these details are piling up: personal health, fitness data, our daily comings and goings, the inner lives of our families and our homes. So you name it. Many people are simply unaware of how much privacy they have bargained away every day. So even if you are sharing some pic on your social networking account, so you are bargaining your privacy in some way or other. And with blockchain technology, we retain much more ownership over our data. We can protect our personal information, giving away only what's required in any social or economic exchange. So anytime we choose to give data of value, we can be compensated for it as well. So you have to be very careful while exchanging your personal identities, even if it is an image or some other thing on your social networking account. So because you never know who is trolling over your Facebook account and what he is influencing out from your day-to-day activities. Then the next one is preservation of rights. So blockchain breakthrough is strengthening property rights by making them inaugurable and unforgettable. So using public key infrastructure, the blockchain not only prevents the double spend but also confirms ownership of every coin in circulation. So that avoids double spending problem. So the implications of how blockchain treats personal right. To enforce right, those rights must be clear. Rights and responsibilities can be codified in a smart contract and placed on the blockchain. In that way, the necessary decision and incentives will be transparent and they will be reached by consensus. Now, to be sure, this is not simply about technology. It is much bigger than physical assets, intellectual property, or any privacy tools. We need better education about rights and we need to understand right management system. And the last one is inclusion. So the blockchain breakthrough is making a stable payment system available to all, regardless of whether they live or how much money they have. So Satoshi Nakamoto designed the Bitcoin blockchain system to work on the internet, but it can operate without it if necessary. Satoshi imagined the typical person would interact with the blockchain through what he called simplified payment verification mode. So this mode works on cell phones. So it lets anyone with the flip phone participate in the market as a producer or consumer. There is no bank account required, no proof of citizenship, birth certificate, or even a home address, no identity. You don't even need a stable local currency to use blockchain technologies. So the implication of how blockchain makes economy more inclusive. So our economies are growing, but the middle class is shrinking. The foundation for prosperity is inclusion. So, and blockchain can help. Of course, inclusion has multiple dimensions. It means participation by people of all social, economic, and racial background. So it means an end to discrimination based on health, gender, sexual identification, or sexual orientation. It means dropping barriers to access because of where a person lives, whether a person is spent a night in jail or how a person voted. It also means an end to glass ceiling of the old boy network. It means change for the betterment. So these are few design principles. So which we need to discuss and which are very important here. So due to the shortage of time, I'm like quickly running through a few of these slides. So then we need to discuss different attack and their solution. So we have this tempering of blockchain. So each block is mined after doing some work. So blockchain together contains a large amount of work. So if an attacker wants to change any block, he needs to compute all the hashes in the block, because one block is connected to the previous block hash, and like this the whole chain is connected to in the blockchain. So this will need a large amount of work, which is difficult with the current hardware. So then the double spending problem is there. Then we have Sybil attack, and we have denial of service attack. So we have different solution like no forwarding of orphan blocks, no forwarding of double spending transactions, no forwarding of same block or transaction. Then we have a disconnect appear that sends too many messages. Then restrict the block size to 1 MB. Then limit the size of each script up to 10,000 bytes. Then we have proof of work, which we have already discussed in my previous slide. Then we have hash cache proof of work. So this hash cache proof of work is a system used to limit email spam and denial of service attack. And more recently, it has become known for its use in Bitcoin and other cryptocurrencies as a part of mining algorithm. So as I have told you in my previous slides, that blockchain is a gradual evolution. It is not a random evolution, or it develops over the time. So this hash cache was used in in cryptocurrencies, and it was proposed in 1997 and Adam Back to limit the email spams. So this is something about hash cache proof of work. So it is the header of the hash cache proof of work. So it makes this is now being used by some cryptocurrencies. So it is also used in Bitcoin mining, spam filter, and comment spanning prevention. Then we have monopoly problem. So this monopoly problem exists because miners are getting less rewards over the time. So they are discouraged to join as a miner. So as I've told you, over the period of time, this incentive mechanism get changed, and now the miners are getting less rewards as they used to get a couple of years back. And mostly all uh, the groups or active participants are there based in China, and it have become the concentrated and now dominate the production of new Bitcoin. So you can see the kind of monopoly problem has creeped in, because a lot of players or producers are based in China. So the difficulty of puzzle is increasing, which is not possible to be solved by normal hardware. So solution for this monopoly problem is now proof of stake, which has emerged as a solution to this problem. So here, person can mine or validate block transaction according to how many coins he or she holds. So depending on the coins one holds, he can validate the block. This means that more the bitcoins or altcoins owned by a miner, the more mining power he or she has. So this is something about proof of stake, which has emerged as a solution to the monopoly problem. Then again, we have proof of burn as one of the possible solution to monopoly problem. Then we have proof of elapsed times also as one of the solution for monopoly problems. So miners, as I have discussed many times or used this term many times. So miners are like you and me, who are responsible for validating a block in the blockchain, validating a transaction and construction of block. We use hash power to vote on consensus and commit transaction with a new block and store and broadcast the block to the peer. Then mining difficulty I have already discussed in my design principles. So mining difficulty. So if I want to create a block in 10 minutes, and we need to ensure that block is getting created in 10 minutes only. If it is creating earlier than 10 minutes, we will increase the difficulty level. And if it is getting delayed, it is taking more time for getting a block to be created, uh, then we will lower the difficulty level so that it gets created in 10 minutes only. Then this is the mining hardware. So these are specialized hardware that are used to solve the cryptographic puzzle. So these are ASIC servers. So these are application specific integrated service circuits which are used to solve this proof of work in a very efficient manner. So these are the ASIC servers, and these are the hardware which you usually use for solving the Bitcoin's proof of work. So we have few applications of permission blockchain as asset moving and tracking, like you can observe of think of supply chain management. Then we have other application in financial services like trade finance, cross-border transaction. In government, we can invest in voting, or we can apply its application in land registry. And supply chain management, we have food safety and global trade. And in healthcare. So participant, this one is the last slide. So this just shows you the evolvement of Bitcoin over the time. So it is not like this that Bitcoin has randomly evolved in 2009. So it is a gradual evolution of Bitcoin. So linked time stamping, verifiable lock. So in early 1980s, it was used to be done by Merkle trees. So digital cash was there in form of e-cash, and then proof of work we don't have. So it was first time evolved in 1997 for anti-spam email, for stopping the email spamming. Then Byzantine failure we used to have there in 1980s to 1985 as Byzantine generals. Then PKIs we used to have in between 1980s and 1985, and a smart contract was first invented somewhere in between 1990 and 1995 by Szabo Eze. So these all are the attributes which make our blockchain: link time stamping, verifiable locks, digital cash, proof of work, Byzantine fault, peak public key as identities, smart contract. So these are gradually evolved over time. So you can see that way long in 1980s, it was first, some of the attributes were first proposed between 1980s to 1985. So gradually over the time, it get changed, and they give rise to this blockchain or Bitcoin, you can say, in 2009. So over the time, it is still changing, and there are few more new technologies to emerge, or more cryptocurrencies to emerge. So that's all, dear participants, for joining this session. If you have any queries, I will try my best to answer your queries, and I'm happy to answer your queries. Yes, over to you, participants. You can ask your queries here. Yes, any
Sir?
query? Yeah, please.
Good afternoon, sir. I don't know whether this is a very basic query. The point is, we were we were talking about this permissionless and permissioned blockchains, And you
Yeah,
were
yeah.
telling in permission blockchain, we can set user roles and things like that so that it is under control. In regard to this, so can I have a restriction of who all stores the blockchain copy? Is that also possible when I say it is a permissioned blockchain?
Yes, so but exactly it is not advisable to do that because it is already a permission blockchain, and your organization or you yourself will be controlling that blockchain, or you will give permission to a set of user to access that blockchain. So it is totally under your control, and it is only as per your requirement that to how many peoples or to how many miners you want to roll out that blockchain. So it again depends on your requirement. If you have more number of transactions, or if you have more number of users, then you can give accordingly the permission to access that blockchain. In case of permission, it is totally under your control. You don't want any replica of blockchain, then also it is fine. If you want a couple of replicas of blockchain, then you are the authorized person to give access to for that blockchain, who can access that permission blockchain. So it
Okay.
totally depends on you in permission
Okay.
blockchain. So it is not a issue at all. Every rules are governed by you. Every rules are decided by you. So it's totally depend on your requirement.
So basically, if I'm going to do things like that, it almost becomes like the centralized database system, like one person or a few people only maintain the blockchain. So how is it then going to be advantageous? You say it is not right to do such permissions, sir?
No. Centralized is something. If means uh, if I talk of permission blockchain, that doesn't mean that the permission blockchain is centralized. Okay. By centralized, we means that only single authority is governing, or there is some kind of single point of failure. So if one node come to halt or one miner come to halt, no other the services are coming to halt, means services shuts down. No one can access that service. No, it is not like this. Means suppose you are owning a business, and you are having a permission blockchain for your business. So you have some customer base, so those customer are performing the transaction on that blockchain 24 cross second 7. So it should be like this, that though blockchain is permissioned or private in terms of that only a set of user can access that permission, can access that blockchain. It is not that because you are controlling that blockchain, so that's why it is permission, or means you are giving your users, your customers to permission to transact over that blockchain. But you are controlling that blockchain. You are deciding who can perform the right operation on that blockchain, who can modify that blockchain. So that doesn't mean that is a centralized authority. Centralized is something that if one system comes to halt, or if one system shuts down, so your complete blockchain will come to halt. So it is not the case in your scenario. So your blockchain, you can either take it as a service from IBM or Microsoft Azure, or you can host your blockchain over some type of cloud infrastructure which is available 24 cross 7. So these are two different things that governing blockchain by you, and a single point of failure. So governing blockchain by you is something that it is under your control, and it does not have anything to centralize authority. Centralized authority, it means that our network is centralized. So here the network we are talking of is completely decentralized network, because blockchain is totally built up on a peer-to-peer decentralized network. So that is no single point of failure is there. And about permission blockchain, it is you who are deciding that who can access the blockchain, and who are the customers who can perform the transaction on the blockchain. So these are two different aspects. One is networked, that our blockchain should be based on a decentralized peer-to-peer system. And second thing is permission blockchain. It is about the accessibility of that blockchain, who can access that permission, and in what manner they can access that permission. So I hope you get a
Yes,
bit.
sir. Yeah,
So these
yeah,
are
I get it, sir. Thank you. Sir, I have another query too, sir.
please.
We have this orphan blocks in the open block system. So is there any way that we keep track, or we get to know how many orphan blocks have been created? Some kind of idea, or do we get to know that? Is there any way that is?
Uh,
Or only the
mm,
miner gets to know that it was ejected?
Yes, exact. So this is something I have discussed this about transparency or abstraction. So this is something means you can what useful thing you will get out of those orphan blocks. The first point is this. So in my opinion, there won't be any useful thing you can get out of those orphan block, even if you get the knowledge of those orphan block, that how many orphan block exist in the blockchain, because orphan block are immediately or after some time will be
Yes.
sent back to the mining pool,
Okay.
and they will be mined again by the miners, and then they will be added to the blockchain. So orphan block, it may be a result of some kind of malicious activity being done on the blockchain. It may get created because of double spending problem. It may get created because of tie up. So as per my opinion, means if you want to means if you means you won't get anything knowledgeable, or you can't make use of those things in some way or other, even if you get the knowledge at how many orphan blocks are being created and at what moment of time it is being created. So even if it is abstract to you, then also it is good, means until and unless you specify your purpose, that I want to do a research, or I am doing a kind of survey, and I want to prove some bitcoin to be better than other in terms of lesser number of orphan blocks. So you can make use of that information in that type of comparison, that this bitcoin is creating less number of orphan blocks, and that bitcoin is creating more number of orphan blocks. That kind of comparison can be done, but you need to find that what more knowledgeable can be infer out of keeping the count of by keeping the count of orphan blocks.
No, I was just looking because every block creation involves so much of processing and computing energy resources. So, if a
Hmm.
system is going to be generating a lot of orphan blocks, basically we cannot be scaling it up to a real-time system.
You are right.
So
You are
that's
right.
why I
So,
was like wondering.
means maybe I have discussed somewhere in the slide. So it is not that easy that every time
Mm,
the orphan wall block will get created. So the probability is 10 to the power minus uh, 10 thousand lakhs that orphan that there will be a tie. Yeah, orphan block will get created in only in case of ties are there. Ties means there is a coincidence that two miners at the same time they win the puzzle. Okay, tie is
mm.
there. So if tie is there, then only the orphan blocks will get created. So this cryptographic hash puzzle is designed in such a way that it rules out the possibility that two miners simultaneously will be able to solve that cryptographic puzzle. So the probability of getting that puzzle solved simultaneously at the same time is close to negligible. So
Okay.
there won't be many cases that orphan blocks are created too often. So orphan blocks will be created, means you can say negligible, one in 1 lakh, one in 10 lakh, one in 1 crore, something like this.
Okay. Okay.
So
So
it's
thank.
probability of get, because I completely agree that there is a lot of resources being spent in solving that cryptographic puzzle in terms of computation, in terms of electricity, in terms of time. So even if orphan blocks gets created, it's a wastage of such resources. So cryptographic hash puzzle is designed in such a way that those orphan blocks are close to negligible.
Okay, sir. Thank you, sir.
My pleasure. Yes, anyone else?
Sir, I have a question. You
Yes.
said that in a blockchain, as the block gets older, when you're dealing with the security design principle, that time you said that as a block gets older, you showed us a diagram also. As a block gets older, it gets more secure. How is that, sir?
Look, now we have discussed few attributes of a block. So it consists of index position. It
Yeah.
consists of it is connected to the previous hash of the previous block,
Yes, sir.
and it contains few more attributes. So like uh, because as I have shown you, the block the newly block the block which is created recently, So it is more prone to attacks because you need to search a block, or you need to, how you will search a block. So you need to have some information about that block, either by transaction number or by block nonce or by hash of that block. So even if you somehow manage to find some block, now I'm saying that means as per per the availability in the literature, they are saying that as the blocks gets older, it becomes more secure. So the thing is that if you want to, if you try to temper that block, so first thing is that it is not very much easy to temper that block. And even if you somehow get to temper that block, then that block will get invalidated. Okay, and once that block get invalidated, in turns the whole blockchain will get invalidated, because blocks
Sir,
are
all that is fine. Sir, all that is fine, sir. I'm just asking how it gets more secure when it gets older. That's all I'm asking.
okay. So it's all about that because on the blockchain you can only means the readily available block that is visible to you is the newest blockchain, because whatever you are adding to the new block. So you are adding, you are not modifying, or you are not adding to the previous block. So the newest block will be connected to the next block. So once a block is already older, it won't be getting in touch, or it won't be easily visible to you, because only the blocks in last 10 blocks can be.
Sir, how can that be? I might have to access information. If a block is not going to be accessed at all, why is it existing? It might have to be accessed for information, isn't it? It might be accessed greatly. Even if it is older, you might have to access that in various applications that you talked
Okay.
about. Those have to be
Okay.
accessed. So how
Okay.
can you
So
say
I will get back to you. You can
okay,
get in
sir.
touch with me, or you can drop me your details, your email. I will get in touch with you.
Okay, sir. Right. Thank you so much.
I will try to be more accurate on this.
Okay. Thank you, sir. Thank you.
It's okay. Yes. Anyone else? I can help you out with your queries.
Okay, so now no questions, sir.
Okay.
So
Thank you
thank
again,
you
sir.
so much, sir. And on behalf of organizing committee and the participant also, that we are very much thankful to you to give the time for these two nice sessions where you delivered so many technical things about the blockchain consensus algorithm and the security. Major concern is security. Okay, so thank you so much, sir.
Thank you,
Thank you,
sir.
sir.
Thank you. Thank you all participants, and it's really my privilege to have this session for you all. Thank you, Akhilan sir. Thank you all
Thank you, sir.
participants. Thank you all organizers. You can get in touch with me, and Akhilan sir will provide my details, share my details with you. And I will share my slide with Akhilan sir. You can get those slides with you. Thank you. Thank you, sir.